Okay, here we are working a piston problem. In the engine system shown, L is equal to 250 millimeters, so 0.25 meters, and B is equal to 100 millimeters, 0.1 meters. The connecting rod BD, B to D, is assumed to be 100 or 1.2 kilograms. So the mass of BD is 1.2 kilograms. And the slender rod is attached to a 1.8 kilogram piston. Mass of piston equals 1.8 kilograms. During the test of the system, crank AB is made to rotate with a constant, which means alpha for AB is equal to 0. Angular velocity, AB, angular velocity, 600 RPMs. And you can transfer that into 62.832 radians per second. Clockwise. All right, clockwise, so a minus K. With no force applied to the face of the piston, okay, we aren't applying any forces here. Determine the forces exerted on the connecting rod at B and at D. So I want to look at this connecting rod when theta is equal to 180. So here's theta. If theta is equal to 180, we're going to have A stay where it's at and B be flat along the x-axis, and DB is going to come down and be flat as well. So this is just pulling out and it's going to be located over there. All right. Neglect the effect of the weight of the rod. So in our answer, we want to know what's going on with the rod DB, and we can neglect the weight. So the weight of the rod is insignificant compared to the forces that it's going to be experiencing on either end. Let's work with a traditional coordinate system. And we are going to be looking at D and B. Let's just go ahead and put in dy, dx, by, bx, kind of arbitrarily. And in this system, we are going to have to deal with an angular acceleration as well as the acceleration of the center of mass, g. Let's go ahead and put the center of mass, g, and a mass times acceleration. I'm going to have it working opposite, assume that. I'm just assuming a direction here. I don't know where my acceleration really is until I run my calculations. And when it comes to an alpha, I'll go ahead and assume a positive alpha for BD. Okay. That should be everything that I'd have to worry about on that system. I'm going to have a crankshaft where I would have, well, really, it's going to be flat. So let's draw it flat. It's going to be like this. And we're going to have equal and opposite. If I assumed positive there, I would have a by and nope. This is connected to this. Yes, bx. And over here, I would have an ay and an ax. And this, we were told, has an angular acceleration of 0. Alpha equals 0 here. And then an acceleration component. And again, I'm just going to choose an arbitrary direction. The normal acceleration component is often, and I will indicate this by Q, the mass at this point in the acceleration of the center of mass. Okay. And then finally, the piston. We're going to have the piston, and in the center of that is D. And so I'm going to have dy and dx, opposite of what I assumed for my rod. And we do have weights, but they said I can neglect the weight. I am just going to put the weight on here in case there's times where you cannot neglect the weight. So that is the free body diagram with all the weights in there. And there would be a normal force that's holding this up. And if we look at our acceleration components, I'm going to put mass of d times the acceleration of d, directed that way because it's constrained. And there is not going to be rotation of the piston. That just isn't possible the way that it's constrained. So there is no alpha for the piston. Let's look at finding out what we can one step at a time. Ultimately, we're going to try to find the forces dy, dx, by, bx. What's going on at the end of the rod? Dy, dx, by, bx. I'm going to start off with finding acceleration. And I know my relative motion equation. Acceleration of B is equal to the acceleration of A plus the acceleration of B relative to A. The acceleration of B, therefore, is going to be equal to, this goes to 0 because A is not moving. It's anchored in place, so it's not translating. That would leave my alpha R of B relative to A plus the omega crossed with the omega crossed with R of B relative to A. And this is for this rod that I was given some information about. That is why I'm starting there. Okay, I was told that it had a constant velocity. So this term, the tangential term, also goes to 0. And that leaves AB equal to the omega of minus 62.832 K crossed with omega 62.832 crossed with R of B relative to A. So what is R of B relative to A? If B is down here because theta is equal to 180, then B relative to A is plus I, and the distance is 0.1. So let's put that in there, 0.1 I. If we work through that cross product, we're going to get the acceleration of B is equal to minus 394.6 I. And that's in meters per second squared. With that information, I am going to be able to find the velocity at B. Velocity at B is equal to omega cross R. And that means my omega is the same omega of minus 62.832 K crossed with my R component, which is 0.1 I. If I work that cross product, I find out that the velocity of B is going to be minus 6.283 in the downward J direction, meters per second. So that means that this has extended all the way flat. It has been moving in this direction, clockwise, and it is now at a point where theta is equal to 180, and the residual velocity that it's experiencing at that instant is minus 6. So this would be where the velocity at B is equal to minus 6.283. What can I do with that? I can start finding information coming from the other direction. Let's look at the velocity of D. What can we find out if we work on the other half of the piston? Velocity of D is equal to the velocity of B plus the velocity of D relative to B. So I found the velocity of B here. Velocity of D is going to equal the velocity of B, which is minus 6.283 in the J direction, plus omega of BD crossed with R of D relative to B. Now D relative to B is going to be in the minus I direction. So R of D relative to B is going to be equal to minus 0.25 I. And do I know an omega for BD yet? I do not, but I might be able to figure something out. Let's put my velocity of D equation together the best I can. So I'm just copying down the velocity of B again. I'm going to add that to my omega BD, and I'm going to assume a positive K direction and cross that with a minus 0.25 I. All right. If I look at working this cross product, a plus K and a minus I is going to give me a minus J component. Let's see, plus K and minus I. K and minus I. All right. So I am going to end up with let's see, VD is equal to minus 6.283 J. And it's going to be a plus, let's see, K and minus Would be a minus. Can I say that? Yeah. Minus 0.25 omega BD. And that's going to be a J component. All right. What do I already know about the velocity of D? I know that it cannot move up or down because it's constrained. It's a piston. So I know that the velocity of D in the y direction has to be equal to 0. That means that if I look at my terms here, I have no I component whatsoever for the velocity of D. So the velocity of D in the I direction, dx, is going to be 0. And the velocity in the y direction is going to be 0. So we're basically breaking it into I and j components. If I have 0 equals 0, nothing in the I direction, and 0 is equal to minus 6.283 minus 0.25 omega BD. Okay. So if I work this, I can solve for omega BD. Omega BD is going to give me an answer of minus 25.133 K. And that's radians per second. Now I can start figuring out some information in relationship to the acceleration at D compared to what I found out about B. So the acceleration of D is equal to the acceleration of B plus the acceleration of D relative to B. Let's put in the terms that I know. I know the acceleration of B, and that was found right here, minus 394.6 I. And what is the acceleration of D relative to B? And that's where I have to add my alpha of BD crossed with R of D relative to B plus omega BD crossed with omega BD crossed with R of D relative to B. Well, I know my angular velocity terms, and I can find the position vector of R of D relative to B. I guess I did that up here already, and that is going to be equal to minus 0.25 I. And then we can start plugging those values in to be able to find the acceleration and the angular acceleration for this rod BD. All right. So let's look at this term right here. And we're going to have acceleration of D is equal to minus 394.6 I. If I assume a plus K direction here, then I'm going to have plus K crossed with a minus I, and that is going to give me minus I and minus J. So this comes out minus J. So that is going to be minus 0.25 alpha BD in the minus J direction. And let's put in the values that I know for the angular velocity for BD. That is clockwise velocity of a minus k crossed with minus 225.133 k crossed with a minus 0.25 I. Okay. Now, if I work this cross product right here, I should get a plus 157.9 I for my normal component of acceleration. And I've worked this already. And if I break this into the I and j components, I and j and I collect them, my acceleration of d in the x direction is going to be equal to all the I terms. And so I use this one, and I need this one, plus 157.9 I. If I look at the j terms, once again, I can't accelerate in this confined space. So there is going to be no movement in the y direction. And my only y component is the angular or the tangential acceleration of a minus 0.25 alpha BD. So that means my alpha BD is going to be equal to 0. My acceleration for D in the x direction is going to end up being these two terms added together, which ends up being a negative 236.7 I, and that's going to be in meters per second squared. So I found the acceleration of D. Now let's look at the acceleration for the center of mass for the rod, which we are concerned about. Back to that rod, and we've got D on one side, and we've got B on the other, and we've got G in the middle. So if we find the acceleration of that center of the rod, we're going to have the acceleration of D plus the acceleration of G relative to D. I know what the acceleration of D is. I just found it right here, 236 in the negative I direction. So acceleration of G is equal to minus 236.7 I plus alpha BD crossed with R of G relative to D plus omega BD crossed with omega BD crossed with R of G relative to D. I already learned that my alpha for BD is going to be 0. So this term goes to 0, no tangential velocity, and that's common for a rod. 236.7 I, and let's put in our omega BD terms. So go back, look at what omega BD was. It was minus 25. Minus 25.133 K crossed with minus 25.133 K crossed with G relative to D. Okay, now I've got a new position vector, R of G relative to D. When it's all flat, the center of this rod is going to, that's going to flip over. We're going to be somewhere around there. G, the center, relative to D, is going to be to the right. So it's going to be a plus half of the length of the rod. Okay. And so that's going to be equal to 0.125I. We can put that in right here, plus 0.125I. And then we just have to work these cross products, and we will get an answer for the acceleration of the center of mass of the rod equal to a minus 236.7I and a minus 78.95, or 6, rounded off a little bit. And that's also going to be in the I direction. Plus minus K crossed with a plus I gives minus J plus I, and then minus K crossed with minus J is going to give us a minus I. So we add those terms together, and we should get a minus 315.658 I. And again, meters per second squared. Now, we found all of our accelerations that we need. We've found all the velocities that we need. Let's start looking closer at our forces. So if I have that piston again, and I know that the mass of the piston multiplied by the acceleration of d is going to be the right-hand side of my equation. And I will just assume that my dx is going this direction. I can sum forces in the x direction. I'm not too worried about the weight. There is a weight term, there is a normal force, but it's not accelerating anywhere up and down in the y direction. So those just essentially cancel each other out. And the rod that's connecting to the piston is causing it to have to move in the x direction. So whatever's going on with dy, weight, and normal force isn't really relevant for what I ultimately need when they told me I can neglect the weight. We can sum those forces if we want to, but let's focus on what we need. Summation of forces in the x direction is going to be equal to the mass of the piston times the acceleration of d in the x direction, and it is only an x component. So dx, I have going in the positive direction. My mass is going to be 1.8 kilograms for the piston. My acceleration of d only had an x component, so that is going to be minus 236.7. Minus 236.7, and that has only the I component. So if I look at dx, I am going to have a minus value. Dx is equal to minus 426.35 newtons. What that means is the direction I assumed for dx is not the direction that force is going. What is really happening is dx is really going in that direction, which makes sense. The rod is pushing on the piston, and so this is from the rod. And then the piston is pushing back on the rod. Frames and machines, equal and opposite. So we're going to have dx from the piston pushing back on the rod. And if that's the case, this rod has to be in compression. So we're going to have a bx. If you look at how this is going to move, the crank is pushing against this center rod, and the piston is pushing against that center rod, and it's in compression, not in tension. So if we sum the forces in the x direction for the rod, and we have an acceleration for g, which we would have found right up here, and that was in the negative I direction. So we had the acceleration of mass of the rod multiplied by AG for the rod. We are going to set that equal the mass of rod times AG. So I'm going to have a plus dx. And what do I have right here? I have a minus bx. If you chose bx going in that direction, I mean, that would be fine. It would work out, and you would just get the negative number. The mass of the rod is 1.2 kilograms. The acceleration of the center of gravity of the rod is minus 315.658 I. And if I put my dx value into here, so dx I know now has to be going to the right. This is set 426.35 minus bx. And if we multiply that together, the 1.2 times the 315, we'll get a minus 378.79. Okay. If we solve for dx, we are going to bring this over, and that's going to be a negative number. And so negative bx is equal to a minus 805 newtons. And the negative signs drop off. So bx is going in the direction that I assumed right here, because it didn't end up being a negative number. Now, if you would have put a plus bx here, you would have gotten a value of minus bx, telling you that it is indeed going to the left in the minus direction. Okay. Now, if we were going to work on putting together the final solution, what it would look like is we were asked for the forces on either end. And so we are going to have 426.35 newtons here, and we're going to have 805 newtons there for B and D. This would be your final answer. Now, if you Okay. Now, if we want to look at the final answer, this right here is going to be what the ultimate final answer for the forces on the rod when you're neglecting the weight. But what if they said you could not neglect the weight? Then we would sum forces in the y direction for the piston area, and we would set that equal to the mass of the piston multiplied by the acceleration at D. And now what we know for a free body diagram, we found out that dx is pressing from the rod in compression onto the piston. So that means that we are going to be coming in a downward direction from the rod whenever it's functioning. It's not, the rod is never going to be lifting up the piston. So our dy component and the actual free body diagram of the piston is going to be a dy going down and a dx going to the right from the rod pushing. We're going to have a weight, we're going to have a normal force, and we do not have any acceleration component. So let's look at summing up our forces in the y direction. If we have a minus w, a plus n, a minus dy, and that's equal to the mass times, there is no y component for the acceleration, so that goes to 0. We're left with the weight of the piston, and the piston was 1.8 kilograms. And so we need to multiply that by 9.81 to get it into newtons, plus n minus dy equals 0. And this is just your statics, another frame and machine type of problem. Equal and opposite. So our dx was going this direction. Our dy is going down here. It has to go up here. dy. And we do have motion for the center of gravity, but it's all in the x direction. We've already calculated that acceleration. And then over here at B, we learned that we have the 805 for our BX, and we have to think about what would be going on here when we have this crank pressing on to the connecting rod DB. And so I am going to say that we have positive for our dy. And then let's say that we have another positive for our by. So this would be lifting up, causing that end to go up. And that puts it in compression. So we could sum the forces in the y direction for the rod, and that's going to equal the mass of the rod multiplied by the acceleration of the center of mass in the y direction, which is going to be 0. The only thing working on this rod is going to be gravity in the y direction. And so we'll have the weight of the rod is a negative. We'll have plus the dy and plus by equals 0. And if we look at the weight of the rod, 1.2 multiplied by 9.81 plus dy plus by equals 0. We have 3 unknowns, so we need one more equation. So we would sum moments around the center of mass for the rod, and we would say that's equal to I bar alpha plus MAD. All right, so if we were going to calculate the I bar would be equal to 1/12 times the mass, 1.2 kilograms, multiplied by the length of the rod, which is 0.25 meters squared. And that would give us an I bar for the center of gravity. That is going to be equal to 0.002625. And if we look at our alpha for the rod, we found that that alpha of BD is equal to 0. So that cancels out that term. All we would be left with would be the MAD. But since our MAD, there is no D distance. This D is the distance between where we are summing our moments and the center of mass. So that we are summing our moments at the center of mass. So that is equal to 0, which zeroes out that term. Also, there is no component for the acceleration of the center of mass in the y direction. It's only in the x direction. So all of that goes away. That means that if we're summing moments at g, we're going to have our component from g over to d in the negative I direction equal to 0.125 minus I. And we're going to have that crossed with dy, and we've got that going up in the plus j direction. And on the other side, we're going to have plus 0.125 in the I direction crossed with another plus by, and that is going up in the y direction equals 0. So if you look at this and work it out, we're going to have minus I crossed with a plus j, which is going to give us a minus k component, a plus I and a plus j, which is going to give us a plus k component. And if we move it to the other side, we are going to get something of 0.125 by in the plus k direction is equal, the negative goes away, 0.125 dy in the k direction. And so by is equal to dy. And if we bring that information back up to here, we will find out that 1.2 times 9.81 is going to give us a minus 11.77 plus 2 dy, since dy and by are equal, equals 0. And so our dy is going to end up being a positive 5.886 newtons up. And that is going to be by as well. And if we wanted to find the normal force over here, again, it's just a statics problem. We would end up with a minus 1.8 times 9.8 would give us a minus 17.66 plus n minus dy, so minus 5.886 equals 0. And that means if we solve for n, we're going to have these added together, negative, other side positive, n is going to be equal to 23.55 newtons up. Okay. So that is, if we were going to be particular, our final answer, we do it in this color, would end up being 805 for our bx newtons, and we would be going up, and we would be going up the 5.886 newtons, and we have our center mass. We would have our mass times the center of acceleration of the center of mass, we would have our value for dy, which would be equal and opposite of what's going on at the piston. So that would be 5.886 newtons. And then we have our dx, which is going to be 4 to 6.35 newtons. Those are all the forces that are acting on rod DB.